Kinematics in one dimension going to be the topic of this lesson. We're really going to do some hardcore problem solving in the area of kinematics, specifically in one dimension. And this is where some students begin to have a little bit of trouble, but my goal for this lesson is that you really get a good intuitive feel for much of the material as well as a systematic approach for problem solving. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. Now, in the last lesson on displacement, velocity, and acceleration, I hinted toward the fact that we might do some calculations involving two different scenarios. And the first is constant velocity, where you have no acceleration. And the second was going to be when you had uniform acceleration or constant acceleration. And then I said, but you're not going to be doing any problems where you have varying acceleration. Well, there's one caveat to that. If you're taking a calculus-based physics class, you might. You still might not, but you might. But for an algebra-based physics class like the one we're going through here, you're not going to be dealing with a varying acceleration. So in the two situations we will deal with, so again, no acceleration, again, you're moving at constant velocity, or with a uniform acceleration, a constant acceleration, these are the two situations, and it turns out there's only a handful of equations for which you're going to do kinematics calculations. And what's nice is when you don't have an acceleration, there's one equation. That's all you got. So we'll see that this equation is related to the definition of velocity. So, but even with uniform acceleration, constant acceleration, you've only got a handful of equations, but it's enough to where some students get to the point where they just are given a bunch of quantities and a problem, and they just don't even know where to start. Well, the good news, again, is that there's a limited number of equations, and even if you just kind of systematically worked your way through all the equations because you recognized it was uniform acceleration, you'd eventually figure some things out. But hopefully we kind of demystify this, and we're going to give you kind of a systematic foundation for kind of approaching this, as well as a little bit more of an intuitive understanding of what displacement, velocity, and acceleration are and their relationships to each other. All right, so before we dive into some calculations and some problems that we're going to solve throughout this lesson, I just want to kind of look at these lovely quantities and kind of see where most of them come from. So if we take a look at the first one here, so delta x displacement equals velocity times time. And again, this really is just coming from the definition of velocity. If you recall, velocity was equal to delta x over delta t, displacement over time. And if you rearrange this, you can get delta x equals v times delta t. So, and in fact, some people actually write this, and I say some people, some textbooks write this as delta x equals v delta t. So, but I'm going to leave it as t. It's pretty common to see it this way. And the idea is that if delta t is t final minus t initial, where t initial is 0, then all you've got is t final. And if that's the only time point you have, then we can just call it t. We don't have to actually signify it something else. And so that's where this kind of reduces down to this form right here. So when you've got no acceleration, you're at constant velocity. This is the only equation you got. Nothing else to worry about. All right, so if we take a look at uniform acceleration, so now your speed is not constant. It is changing, but it's changing at the same rate the entire time. And you've got a very similar looking equation where you can't just use the velocity because it's changing. So it's either always going up or always going down. It's not at one set point, but what you can do is you can use a directly analogous equation in which you use the average velocity. And if you recall in the last lesson, we actually came up with an equation for the average velocity where we said that the average velocity was equal to v initial plus v final over 2, or 1/2 times the sum of v initial plus v final, or something like that. Also, one thing to note, I said you might see v initial and you might see v naught, and all my equations are written with a naught. So I'm going to try and use that here, but again, that essentially means velocity at time 0. So when you see that little naught symbol, it means at time 0. All right, so, if we can calculate the average velocity because we know both the initial and the final velocities, then we could use this equation, and it would be very analogous to what we're doing with no acceleration. Now, this next one's a little bit different here, and so it turns out it's not going to be easy for me to show you where it's derived from, at least not the second part of it, because it actually does come from calculus, and it involves taking a second derivative, which we're just not going to do in this algebra-based class, but we could. So, but the idea is this. So, if you ignore that last term, this looks pretty much a lot like both of these. So, but the key is that, if you just use your initial velocity, well, the idea is that velocity is changing the whole time. It's either going up or going down. And how do you account for that? Well, that's what this last term does. It accounts for it. And so if you're speeding up, so then, along with that initial velocity times time, you have to add an additional term to get an overall higher displacement because your velocity has been going up, so you're going to go further and further and further, and definitely further than if you just maintained that initial velocity the entire time. On the other hand, if you're slowing down, well, if you're slowing down, that would actually mean you have a negative acceleration. We'll get into this a little bit. But if you're slowing down, that means your acceleration and your velocity point in opposite directions. And that means you need to make one positive and one negative. And it's customary at this point to make the velocity positive and the acceleration negative. And so in this case, you'd be plugging in a negative number for A right there. And so you'd end up with this first term, and then you'd be subtracting or adding a negative term overall. Now, one thing I just want to bring this up and give you one caveat is that a lot of textbooks will take this and give you a fifth equation, and they'll have v naught t minus 1/2 at squared. And they'll say, well, always plug in a positive value for a. You just have to choose the right equation. If you're speeding up, it's this equation. If you're slowing down, it's this equation. If you're accelerating, it's this equation. If you're decelerating, it's this equation. So I hate that. I really do. So we're going to make a point of making, of making terms positive, negative a lot of times and stuff like that throughout this course, especially in kinematics. And as a result, I just find no need to include this equation. Giving students an extra equation often adds to the confusion. Making them realize there's only 4 uniform acceleration equations usually puts a smile on students' faces. So I'm not going to use this equation. So what I'm going to do is input an acceleration that's either positive or negative right there. And if you're speeding up, then the acceleration and the velocity are in the same direction, I'll make it positive. If you're slowing down, decelerating, then the acceleration and velocity point in opposite directions, and I'll make the acceleration negative in that case. All right, also not going to show where this one's derived from. This is my least favorite of the equations. So it's my least favorite because it has squares in it, and that makes it a little difficult sometimes to do the math in your head. And I like doing math in my head when I can. But definitely we'll plug and chug with the calculator when appropriate and things of the sort. But one thing that's nice about this equation right here is this is the only one of all the equations here that does not have time in it. Notice this one has time in it, this one has time in it, this one has time in it. This is the only one that does not have time in it. And so if you're doing a calculation involving uniform acceleration, but you don't know anything about the time, that might be the indication that this is the lovely equation you're using. And then finally, this last one here, just like these first couple were a rearrangement of the definition of velocity, this last one's really just a rearrangement of the definition of acceleration. So if you recall, acceleration was equal to the change in velocity over the change in time. And so what you might see is that acceleration equals v final minus v initial all over, and again, it's really t final minus t initial, but if t initial is 0, then it's really just t final, but if there's only one time point, we'll just make it t. So at that point, so it's like t minus 0. And then rearranging it, we get a t equals v final minus v initial, or v final equals v initial plus a t, adding it to the other side. And notice that looks just like that in reverse. So that's just really a rearrangement of the definition of acceleration. And in fact, if the numbers are nice, I would recommend that if you get an intuitive feel, you might not even need this equation because you understand what acceleration actually means. And we'll demonstrate this throughout this lesson. All right, so now we've seen these equations. Again, the first thing you're doing in approaching any kinematics problem, is first you're going to ask yourself a question. Is no acceleration, i.e. constant velocity, or is it under uniform acceleration? And the problem is going to have to tell you and clue you in one way, shape, or form. And usually it's going to be by directly telling you which of those two scenarios you're in. Let's do some plugging and chugging. All right, once again, if you're joining me for my master course, all these problems are already typed out for you on the study guides, and there's plenty of room so you can work them out right on there if you so choose. But for the rest of you, I will make sure that the questions are put up on the screen as we go here. All right, so first question here. A car travels due north for 4 hours with a constant speed of 60 miles per hour. What is the displacement? And again, for those of us that are in the States, and that's the majority of my audience, I'm using units you're going to be somewhat more familiar with to start. But we'll definitely be transitioning over to SI units in a little bit. So in this case, travels due north for 4 hours with a constant speed. The moment you hear constant speed, you think constant velocity, no acceleration. That's the only equation we got. All right, and we want to know what is the total displacement. Well, if this is the only equation we got, and it's an equation that involves displacement, then that's the one we're going to have to use. And so in this case, we've just got the displacement equals the velocity times the time, and we'll just do some plugging and chugging here. Velocity was given as 60 miles per hour, and the time was given 4 hours. I did make sure it was in hours so that the units would cancel here. So, and 60 times 4 is 240 miles. So, and there's a good chance you probably did this one in your head without like plugging and chugging going through an equation. Like, well, Chad, the car goes 60 miles per hour. That means every hour it goes 60 miles. So if you did that for one hour, that would be 60 miles. If you did it for 2 hours, that'd be 120 miles. 3 hours, 180 miles. 4 hours, 240 miles. And if you did it that way, and that's the level of an intuitive understanding you have, fantastic. So if you didn't, hopefully that last exercise of 1, 2, 3, 4 hours, how far it went, was instructive. But the answer definitely is the displacement is 240 miles. All right, second problem we'll take a look at, and this one's going to be a little bit tricky. But it says a man travels 60 miles to work one way at an average speed of 40 miles per hour. He travels 60 miles home at an average speed of 60 miles per hour. What is the average speed of his round trip? Now, you might be tempted to be like, well, 40 miles per hour one way, 60 miles per hour the other way, the average is 50, right, Chad? Wrong, it turns out, but we'll see why. It is a little bit tricky. This makes a great multiple choice question on a test because they can put that 50 miles per hour as definitely one of the answer choices, and you might be tempted to just pick it without even trying to work the problem out. But it's not going to work out to be 50, as we'll see. So let's see if we can map this out a little bit. So we've got home, and over here we've got work. And so on his way to work, so 60 miles to work, so that is a displacement, or distance technically, but displacement of 60 miles. And we're told his average velocity is 40 miles per hour. All right, then on the way home, he's just retracing his steps. It's 60 miles back home. So again, that's a displacement of 60 miles. But now, maybe he's avoiding rush hour or something. His average velocity is now 60 miles per hour. Okay, so again, your intuition, if it's telling you the average is going to be 50, again, it kind of looks that way. You're like, well, it's 40 miles an hour on the way there, 60 miles an hour on the way back, the average is 50. Except the problem is he doesn't spend the same amount of time going those two average speeds. So if you look and you say, does he get to work faster or does he get home faster? Well, he's, traveling faster on the way home, so it should take him less time to get home, and that's the key here. He's going to spend less time averaging 60 miles an hour than he does averaging 40 miles an hour. And because he spends more time at an average of 40 miles per hour, the overall average for the entire round trip is going to come out closer to 40 than it is to 60. So 50 is right in the middle. It's going to be lower than 50 miles per hour. That's what your intuition, hopefully in the future, will start to tell you. All right, so we got to work this out here. In this case, whether we've got acceleration here or not, we're not really given any indication. So, but we're given average velocities, and given average velocities, that's fantastic. We can go straight here. And that way, whether he starts and stops and speeds up and slows down all the way to work, it doesn't matter. We've got the only thing we need is that average velocity. We can use delta x equals v average t. And for all we know, maybe he just went constantly 40 miles per hour out of the way work and never stopped. There's no lights, no nothing, whatever. The key is, once we know an average velocity though, it doesn't matter. And we can just go straight to displacement equals average velocity times time. All right, so what we want to do here is again get the average velocity for his entire round trip commute. And so let's put that up on the board here. So the round trip. So, and for the round trip, delta x equals v average t. So if you rearrange that average velocity is going to equal delta x over t, where we need to know the displacement for the entire round trip and the time for the entire round trip. Well, one of those is not so bad to figure out. If it's 60 miles to work and 60 miles home, well, then his entire displacement for the entire round trip, or his entire distance really, we should say, is 120 miles. His displacement would be 0, that's tricky. So about 120 miles for the distance. Notice we're really dealing with distance and speed scalars rather than velocity and displacement here. All right, so 120 miles is his total distance traveled, but the time, we don't have that. So we've got to find the time for on the way to work and the time for on the way home and add them together to get there. And to do that, we're actually going to use the same set of equations here. So on the way to work, we've got delta x equals v average t. If you rearrange and solve for t, you're going to get delta x, let's see if I can write that correctly, over v average, which in this case was 60 miles over 40 miles per hour, which is going to come out to 60 over 40 is the same thing as 6 over 4, which reduces down to 3 over 2, or 1.5 hours. All right, going home, this one you probably see in your head. If he's traveling at an average of 60 miles per hour, then how long does it take him to go 60 miles? Well, 1 hour. But again, you could set it up just the same way and just say time is equal to the distance over the speed, the average speed, which is 60 miles over 60 miles per hour, which is going to get you 1 hour. And then you're simply going to add these together, and 1.5 hours plus 1 hour is 2.5 hours. Cool, and that's what we're going to plug in time for the entire time of the round trip. And so here we've got 120 miles over 2.5 hours, and you can definitely plug this into your calculator. You could also, if you wanted to, and I like doing math in my head when I can, instead of 2.5, I can write this as 5 halves hours. So, and dividing by 5 halves is the same thing as multiplying by 2/5. So 5 goes into 120 24 times 2. It's going to get you 48 miles per hour. That is the answer to this question. Cool, and as we pointed out before, because he spends more time at 40 miles per hour than he does at 60 miles per hour, the overall average velocity for the entire round trip should come out closer to 40 than it does to 60, and indeed that's true. All right, the next question here is a multi-part question. It says a car accelerates uniformly from rest with an acceleration of 10 meters per second squared. What is the velocity after 6 seconds? How far does it travel in the first second? How far does it travel in the second second? How far does it travel in the third second? And the idea is that if this car is speeding up, then it's going to be going faster and faster and faster. And so how far it travels every additional second should be further and further and further. So let's see kind of how we approach this here. So we're told that the uniform acceleration, that acceleration is 10, and notice it says meters per second squared, but you might have intuited that I'm going to write meters per second. So we make that pretty. So that means it's speeding up 10 meters per second every second. Nice round number. It's going to make doing this not so bad. So first question we want is, what is the velocity after 6 seconds? So, and then we want how far does it travel in the first, the second, and the third second. So velocity after 6 seconds, this you can do in your head. So the acceleration is 10 meters per second per second. So we're told it accelerates from rest, which means the initial velocity is 0. It's a big key word, from rest. It means your initial velocity is 0. So if you start at 0 and you're speeding up 10 meters per second every second, then 1 second after you start, you should be moving with a velocity of 10 meters per second. After 2 seconds, there's an additional 10 meters per second for that second. Now you're up to 20 meters per second for the velocity. After 3 seconds, up to 30 meters per second for the velocity. After 4 seconds, up to 40 meters per second for the velocity. Again, the key is that the acceleration is 10 meters per second every second, per second. So every second you go further, the velocity goes up by 10 meters per second. That's how this works. And so you're like, well, then what is the velocity after 6 seconds? Well, if you start at 0, it should be 60 meters per second. And hopefully you can kind of see that. But if you understand what acceleration means, that it's just the change in the velocity per second, and it's telling you that it's changing by 10 meters per second every second, then after 6 seconds, it'd be 60 meters per second. After 10 seconds, it'd be 100 meters per second. After 15 seconds, it'd be 150 meters per second. And what you may not have realized, if you're doing it in your head like that, is that you're technically just using that equation without actually having to think about using that equation. And if you can think of acceleration like that, that's exactly where I want you to get. And that's why the problems we're going to do are going to be nice round numbers. Because if instead instead of saying the acceleration is 10 meters per second squared, what if I'd said the acceleration is 1.436 meters per second squared? Well, now all of a sudden the math is tough to do in your head. You're going to pull out your calculator. And all of a sudden it's not going to be this kind of intuitive thing that you're probably doing in your head. But if we start with nice round numbers, then when you do get harder numbers, hopefully you've got some of those intuitive pathways built in, and you might still realize you need to pull out your calculator, but you might recognize what you need to do in your calculator without even thinking about it as an actual equation. So, but if we did use that equation, we'd say that the final velocity equals the initial velocity of 0 plus the acceleration of 10 meters per second times the time of 6 seconds. And you can see, yep, that final velocity after 6 seconds is going to be 60 meters per second. Notice these seconds cancel and you're left with units of meters per second. Okay, so same thing we just intuitively calculated. Now we use an equation to do it as well. Now let's go to the other problems here. And so the question is, how far does it travel in the first second, the second second? And so we want delta x for 0 to 1 second. Or maybe we'll write this a little bit different. So t equals 0 to t equal 1 second. And then we want the displacement for t equals 1 second to t equals 2 seconds. So the second. And then we want the displacement for t equals 2 seconds to t equals 3 seconds. Cool. Now there's actually not just one way of approaching this. There's a few different ways, at least a couple of different ways, and we'll go through a couple of them. But we want displacement. So you got to say, okay, well, which of these equations have displacement? Well, the first three all have displacement. That means you're probably using one of those first three. Probably not using that last one, so at least not directly or initially, as we'll see. But let's just kind of take an accounting here and figure out how we might do this. Well, in this case, first equation, delta x equals v average t. Let's write that out. Well, for that first second, how long a period of time is passing? Well, 1 second. Okay, we got the time. Do we have the average velocity during that first second? Well, we don't, but you might recall again that your average velocity is equal to v initial plus v final over 2. Well, for that first second at time 0, what was the velocity? Well, we started from rest. The velocity was 0. And after 1 second, we haven't figured that out yet formally, but we did informally. We said the acceleration is 10 meters per second per second. So after 1 second, we said, yeah, the velocity at that point would be 10 meters per second. After 2 seconds, it would be 20 meters per second. After 3 seconds, it would be 30 meters per second. And so even though we haven't formally done it, we can calculate it or just reason it out in our heads based on knowing what acceleration is, or use this equation to figure it out and say that v final equals the initial velocity of 0 plus acceleration of 10 meters per second times 1 second, and you're going to get a velocity of 10 meters per second. So even though we're not given what that final velocity is at t equals 1 second, we can intuit it or calculate it very easily. And so yeah, we don't know the average velocity off the top of our heads, but we can get it pretty quickly and totally use this. So the initial velocity was 0, the final velocity at t equals 1 second is 10 meters per second, so the average is going to come out to 5 meters per second. And from there, and again, from 0 to 1 is 1 second, and so 5 meters per second times 1 second, going to get us 5 meters. So from t equals 0 to t equals 1 second, the displacement is 5 meters. So what about for the second, from t equals 1 second to t equals 2 seconds, how far now? Well, again, whatever this object is, it is speeding up and going faster and faster and faster, which means every successive second we should anticipate that it's going further and further and further. Now, we don't know the answer yet, but it's got to be higher than 5 meters, right? Well, let's figure this out. We could do this the same way, and we could rationalize that out in our head. So at t equals 1 second, we already figured out that at t equals 1 second, the velocity is 10 meters per second. At t equals 2 seconds, we're going to be up to a velocity of 20 meters per second. And if you know the initial and final velocities, then the average is halfway in between. Or you can do 10 plus 20 over 2. So, and the average would come out to 15 meters per second. And we could do the same thing and say the displacement equals the average velocity, 15 meters per second. And again, from t equals 1 to t equals 2 is a total duration of time of 1 second. So 15 meters per second times 1 second is 15 meters. And we haven't written anything on the board yet. We just kind of rationalized that out and did it in our head using, again, the exact same equation. Okay, now that's not the only way to do it, but we could have done it that way. And it's 15 meters, it's longer than 5 meters, just like we expected it to be. So, but let's approach this a little bit different way. Let's see if we can go about this route right here. And so in this case, delta x equals v initial t plus 1/2 a t squared. Okay. So in this case, v initial at t equals 1 second is 10 meters per second. I'm sorry. Yes, 10 meters per second. How long is the entire duration of this journey from t equals 1 second to t equals 2 seconds? Total of 1 second. What's our acceleration? 10 meters per second per second. And again, how long is the entire duration of this part of the journey? Again, it's a full 1 second long. And we'll square it. So by the way, big mistake students make is forgetting to square terms, not just here, but in other places, like E equals mc squared. That's another common place where students forget to actually square it. They might write it in the equation and then forget to do it in the math. So this is a key common place where that happens here in physics. So let's look at this out. So notice 10 meters per second times 1 second, that's 10 meters. And then 10 meters per second times 1 second squared is also going to come out to 10 meters. Then times 1/2 is 5 meters. 10 meters plus 5 meters gets us one other way of getting us our 15 meters. So more than one way to skin a cat, so to speak. All right, last one here, from 2 seconds to 3 seconds. Well, from 2 seconds to 3 seconds, we can see again that at t equals 2 seconds, our velocity was 20 meters per second. By the time we get to t equals 3 seconds, it'll have gone up an additional 10 meters per second based on the acceleration and should be up to 30 meters per second, which means the average velocity during that 1 second duration, somewhere exactly right halfway in between, of 25 meters per second. So, and then the whole time is 1 second. So you say, okay, average velocity is 25 meters per second times 1 second, and it should be 25 meters. And again, we just did it in our head. Or we could use this equation again and say, okay, the initial velocity is 20 meters per second times, again, the whole duration from 2 seconds to 3 seconds is 1 second. So we got 20 meters per second times 1 second plus 1/2 times 10 meters per second times 1 second squared. And you're going to get 20 plus 5 and get 25 meters per second yet again. But maybe there's another way we can do this, because displacement also shows up in this equation right here. Now again, this is my least favorite equation. I would never use this one for this calculation. I just want to demonstrate that it will lead us to the same answer. Okay, so in this case, we've got v final squared equals v initial squared plus 2a delta x. So, and this one is kind of the most laborious because again, we've already figured it out that the time at t equals 2 seconds, the initial velocity for this period is 20 meters per second and the final is 30 meters per second. But we had to figure those out, and they're both going to show up here. We would have to figure those out in this one as well. So, and we got to square them, which makes the math big and stuff, and that's not very fun. But that final velocity was 30 meters per second. And so here we plug that in, 30 meters per second, and square it. And in fact, I'm going to subtract off this initial velocity squared as well, and it's 20 meters per second. And then we'll square it, and that's going to equal our 2 times our acceleration, 10 meters per second times delta x here. Well, 30 squared is 900, 20 squared is 400, 900 minus 400 is 500, and then 500 divided by 20, which I might do differently. I might do 500 divided by the 10, so is 50, and then divided by the 2 is 25, and yet again I get delta x equals 25 meters. Get the same answer anyway here. Now, it won't always work out like this, like, oh, you just pick any of the equations. It worked out in this one that we could have used any one of those 3 equations, but which one's the easiest? And personally for me, the easiest one for me was, again, that guy right there. I could pretty quickly, knowing what acceleration actually means, figure out that the initial velocity at t equals 2 seconds was 20 meters per second, and at t equals 3 seconds was 30 meters per second, and at the average is going to be halfway in between at 25 meters per second. And so during that 1 second period, 25 meters per second times a second is 25 meters. That was definitely the easiest way for me, but all 3 of those equations could have worked.